Alright, so let's talk about the very last lecture of the survey of PChem. This one again is for the experiment, and we're going to talk about the spectroscopy experiment, and then we're going to talk about the Beers law. So the spectroscopy experimental setup is usually that you have a light source, and then there is a device that changes the wavelengths, and then select one of the wavelengths, isolate it, and then that isolated light goes through the sample, and then you can detect how much of the light actually goes through that sample. So more you have, more of the stuff you have in the sample, the light either going to get scattered off or get absorbed, so that the detector gets the less signal, and so does the length of the cuvette, that's this one right here. If the beam goes through the longer path, then your light that goes through this sample is going to get less. And also that depends on the molecule. The molecule actually absorbs a certain amount of the certain wavelengths of light, and that depends on the molecule. So that if the molecule has the tendency of actually absorbing the light quite a bit, then that you're gonna lose quite a bit of light too. So to actually summarize all of those stuff, somebody named Beer and maybe Lambert, those guys actually produced the Beers law, and it says that absorbance is equal to epsilon B times C. The B is the path length, C is the concentrations, and epsilon is the value that's associated with the molecule. It's the tendency of the absorbing light, and that's called the molar absorption coefficient. So those three quantities are kind of important for predicting the amount of light that goes through. And what's absorbance? Before I talk about absorbance, I'm going to talk about the transmissions. The transmission coefficient is T, is given by I over I naught. I naught is the incoming light, amount of intensity of incoming light, and then I is the light that passes through the sample. So this is more or less like the amount of light, that percentage of light that goes through that sample. So if you have the diluted sample, the transmission coefficient is going to be large, and then if you have the concentrated sample, then you're going to have the small transmissions. And then absorbance is actually the negative log of T, which is the negative log of the I over I naught. So that's the Beers law right here. So let's just try to derive it, just because this is a PChem class. So we have talked about the changing intensity of the incoming light to the light that passes through the sample, right? So consider the change of intensity over a very small distance dx. And that's this one right here, the change of intensity of light. It might remind you that this is final state minus initial state. So the final state is the amount of light that passes through, and then the initial state is the amount of light going into. That's I know, right? And that's di. So the change is going to be a negative values, right? And then that's equal to the negative times the amount of light that goes into it, and then that molar absorption coefficient, that's the tendency of light being absorbed by the molecule, and then the concentration, And then also the path length, but for this particular case, it's a very short distance, so it's dx here. And then I'm gonna separate the variable I on the left hand side and then x on the right hand side. So we have the di over I on the left hand side, and then everything else is on the right hand side. And then just integrate both sides, you get that and that. The epsilon and concentration is constant, so it comes out. And then if you do the integration on this one, that's log of the I over I naught. And then that's basically the log of t is equal to negative epsilon cb. So if you multiply both sides by negative, you get absorbance is equal to epsilon cb. So that's pretty much all there is to it for the Beers law. So how do we actually use this Beers law? To use it, you have to find out what frequency of the light is actually absorbed by the sample. That will tell you the information on what type of molecule is in the sample. So that's the very first thing that you're going to have to do. And then once you tune the frequency, frequency of the light that matches with your sample, then that you want to take a measurement of the several known concentration which contains the same type of molecule, or actually the same molecule. And then you're going to do the linear fit. That's just like the other experimental technique, right? And then take the measurement of the unknown, and then compute its concentrations from the linear fit equations that you get from the several known concentrations. That's called the standardizations, or whatever the things that you called in an analytical chemistry class. I think that's probably good enough for this one. So,